Why are PCBs green? Why do traces zigzag? Why are there random holes everywhere? These aren't design choices, they're engineering secrets. Have you ever really looked at a circuit board? I mean, really looked. Past the big chips and the shiny components. Why are they almost always green? Why do the little copper lines, the traces, sometimes look like tiny winding snakes? What's with all the holes scattered across the surface? They aren't just random decorations. Every single line, every hole, and every color on that printed circuit board, or PCB, has a very specific job. It's a hidden language of engineering, a visual blueprint packed with secrets hiding in plain sight. Once you start to understand what these details mean, you'll never look at electronics the same way again. These boards are the unsung heroes inside every piece of tech we own. They are the foundation, the city grid upon which our digital world is built, from your smartphone to your car's dashboard. So, let's talk about the color. Most circuit boards are green, that iconic, almost institutional green. This color isn't the board itself, it's a thin, tough layer of polymer called the solder mask. Its main job is super important. It protects the copper traces from oxidizing, and more critically, it prevents globs of molten solder from accidentally bridging two connections during manufacturing. It essentially masks off the parts of the board that shouldn't be soldered, leaving only the shiny pads exposed where components need to connect. Without it, mass-producing electronics would be an absolute nightmare of short circuits and failed boards. But why green? The tradition started decades ago. Early on, the specific resin used for the solder mask had a natural, muddy greenish-brown hue. As the technology improved, manufacturers had more color choices. However, green had a distinct advantage for the human eye. During the manual inspection process, the high contrast between the green mask, the shiny copper pads, and the white silkscreen labels made it significantly easier for technicians to spot tiny defects. Green is smack in the middle of the visible light spectrum, a wavelength our eyes are particularly sensitive to, which reduces eye strain over a long day of staring at boards. Now let's look closer at the traces, those thin copper lines that act as the board's wiring. You'll notice that they don't always take the most direct route. Sometimes a trace will meander across the board in a long serpentine pattern, or a zigzag pattern, even when there's a clear straight path available. This isn't a design flaw or an artist's signature. It's a very clever technique called trace length matching, and it's all about timing. In high-speed digital circuits, like the ones that handle RAM or fast data buses, timing is absolutely everything. Signals need to arrive at their destination at precisely the same moment. Imagine you and a friend are running a race to the same finish line, but you have to start at different points. To make the race fair, the person with the shorter path would have to wait, or the person with the longer path would have to run faster. In electronics, signals travel at a near constant speed. So, the only way to ensure they arrive together is to make their paths the exact same length. If one signal path is physically shorter than the others in its group, the designer has to artificially add length to it. That's what those snake-like patterns are for. The goal is to make the time it takes for an electrical pulse to travel down one trace identical to the time it takes to travel down its neighboring traces. If the signals in a data bus arrive out of sync, a problem known as timing skew, the receiving chip can misread the data, leading to errors, crashes, and system instability. If you keep looking at those copper traces, you'll notice another key detail. They aren't all the same size. Some are incredibly fine, almost like a human hair. Others are thick, wide bands of copper. This variation is an intentional design choice. It tells a story about power and purpose. The width of a trace is directly related to how much electrical current it's designed to carry. It's like a garden hose. It's like a fire hose. One waters plants. The other fights fires. A thin trace has higher electrical resistance than a wide trace. Resistance generates heat when current flows. Push too much current through a thin trace and it heats up. It can burn out and break the circuit like a blown fuse. To handle higher currents safely, engineers use much wider traces. Wider paths have lower resistance and carry more power without overheating. They also spread heat across a larger surface area. Now, let's talk about the holes. Not the big mounting holes for screws, but the tiny, often shiny holes that seem to pepper the entire surface of the board. These are called vias, which is Latin for path or way. That's exactly what they are. Vertical pathways that allow an electrical connection to pass through the physical layers of the circuit board. Most modern PCBs are not single-sided. They are multi-layered sandwiches, insulating fiberglass conductive copper. A simple board might have 2 layers, 4 layers, while a complex one, like a smartphone's motherboard, could have 12 or more. Vias are the elevators of the circuit board. They enable a trace on the top layer to connect to a trace on the bottom layer, or to any of the internal layers hidden from view. Without vias, routing a complex circuit would be nearly impossible. Vias let designers route traces over and under each other on different layers, creating dense, intricate layouts. There are different types of vias too. The most common is a through-hole via, which goes all the way from the top to the bottom of the board. But in more advanced and compact designs, you'll find blind vias and buried vias. The empty spaces left for different product versions are there to support multi-version boards and features that might be added or removed. Reusing a single board design across models saves tooling costs and simplifies manufacturing. Let's move on to the text and symbols you see printed on the board, usually in white ink. This layer of markings is called the silkscreen, named after the screen printing process traditionally used to apply it. The silkscreen layer carries no electrical current. Its job is purely informational, but it's incredibly important for the humans who build, test, and repair the device. Gold fingers, corrosion resistance, curved traces, signal integrity, mounting holes, grounding, multiple layers, complexity. Every tiny detail on a circuit board has a purpose. Once you see it, you can't unsee it. If you like this, there's more on the channel. Think of it like a city map. You have big highways, smaller streets, tunnels, and street signs. On a PCB, wide traces are the highways, thin traces are the local roads, vias are the tunnels connecting different levels, and the white text is the street signs telling you where everything is. It's a beautifully organized system, but you need to know what you're looking for to appreciate the genius behind it. But their design isn't just about connecting point A to point B. It's a complex dance of physics, manufacturing constraints, and clever problem solving. Each choice an engineer makes, no matter how small it seems, directly impacts the device's performance, its reliability, and even how much it costs to produce. Let's peel back the layers and decode some of these secrets. So, let's start with the most obvious question of all. Why that color? Of all the colors in the world, why did green become the standard for the tech that defined an era? It seems like such an arbitrary choice, but the answer is a mix of history, practicality, and a little bit of human biology. It's the perfect place to start our journey into the world of PCB design, because it shows how even the most basic feature has a surprisingly logical story behind it. The answers are all there, etched in copper and coated in a thin layer of protective polymer, just waiting to be discovered. There's also a big economic reason. Once the industry standardized on green, the supply chain optimized for it. Factories bought green solder mask ink in massive quantities, which drove the price down. It became the default, the cheapest and most readily available option. While you can absolutely get PCBs in other colors today, blue, red, black, white, even purple, they are often considered custom orders. They might cost a little more or have slightly longer lead times. Blackboards, for example, Obolin den 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 dim stir, Wazandin, Inkandi din, Hobri den crer, a day the incredibly, stir crabby sleek, but can main green, can make inspection harder, because the contrast is lower. So, the next time you see that familiar green glow from inside a new gadget, you'll know it's not just a style choice, it's a legacy of manufacturing history, a nod to human-centric design, and a practical decision that helps keep costs down. Other colors might be used for branding or to differentiate prototypes from production models, but green remains the undisputed king. Think about the shiny gold-plated contacts on the edge of a RAM stick or a graphics card. Those are often called gold fingers. Gold is used there for a very specific reason. It's highly resistant to corrosion and wear, since these edges are repeatedly inserted and removed from slots. Using gold ensures a reliable, clean electrical connection for years. It's a small, expensive detail, but it's critical for the long-term reliability of any modular component. Here's another one: mounting holes. The big holes in the corners that you use to screw the board into a case do more than just hold it in place. Very often, the metal ring around the hole is connected to the board's ground plane. When you use a metal screw to attach it to a metal chassis, you create a large, stable ground connection for the entire system. This helps to reduce electromagnetic interference, or EMI, that annoying electrical noise that can cause glitches and instability. Even the shape of the traces can have a hidden meaning. Many traces use sharp 90-degree turns, but on very high-frequency boards you might see gentle 45-degree or even curved turns. Sharp corners can cause signal reflections and impedance mismatches at very high speeds, degrading the signal quality. Smoothing out the corners helps maintain signal integrity, ensuring that data travels cleanly without distortion. The most common markings are component designators, R1, C12, U3. These labels correspond directly to the schematic diagram. Assembly machines and technicians use them to know exactly which component goes where. You'll also see outlines that show the physical size and orientation of a component. That prevents the chip from being installed backward. Test points, polarity markings, product name, Rev 2.1, manufacturer's logo. All of these details are crucial for traceability and quality control. The silkscreen is the human-friendly layer on an otherwise machine-oriented object. It bridges the gap between the abstract electrical design and the physical reality of the board. While the copper layers are all about physics and electricity, the silkscreen is all about communication. It's a simple, low-cost feature that saves countless hours in manufacturing, debugging, and repair. The next time you see those little white letters, remember that they are the quiet guides that help turn a bare board into a fully functional piece of technology. Once you start looking, you see these engineering secrets everywhere. The empty spaces left for different product versions, the grids of vias pulling heat away from a processor, the white labels guiding a technician's hand. It's all part of a dense, intricate story of engineering. Now that you know what to look for, you can't unsee it. That green rectangle is no longer just a component. It's a map filled with clever solutions.